I started realizing that it was actually math and science that was kind of the subjects that came most naturally to me, found it more enjoyable. And it was my junior year physics professor, Mr. Bellamy, that kind of totally changed my mind. And he had this reputation for being this kind of very eccentric guy, kind of weird, but like his homework problems weren't just, you know, equations. He was always like flying his motorcycle off the school roof, and you're trying to compute that trajectory, or it was like a roller coaster that went completely off the rails, and you're doing this change between kinetic and potential energy. And I found it was like actually the homework I enjoyed doing and kind of looked forward to it. But the thing that kind of sold me was at the end of the week, we actually got to travel to NASA Ames. And so NASA has a ton of sites around the country, but this one was in the Bay Area in California, and it's really known for having some of the premier facilities. So we got to tour wind tunnels that, you know, are about the width of this room, massive. We got to tour water tunnels, different chemical labs, and what kind of, you know, impressed me was people actually seemed genuinely excited about their job. They were clearly very passionate about what they were doing, and that kind of confirmed that, you know, aerospace engineering is absolutely what I want to do. So I worked as a manufacturing co-op, which meant I was on the floor, I was hanging with the operators, and spent a lot of this time actually going through each individual step to make a turbine blade. I loved it. It was super hands-on, got to learn about all the processes. And a lot of my big job though was you would take your turbine blade, you know, at the end of all these steps, and we would say, okay, what are the parts that aren't good to be sold to people? So sometimes they had like a defect, sometimes they had like a little ding, and there were often patterns. So like, you know, there were tons of these, you know, these blades that had that ding on the top right corner, and it was our job as manufacturing co-ops to go back through the process and figure out what step actually caused that deformity and try and fix it. So it was kind of like troubleshooting, and it was fun. But I discovered that during that internship, I started kind of asking why the blade was designed as it was. Why is that material? Why is it that curve? And the answer I always got was, you know, it is that way it is because it's the way we're told. And started kind of wishing to understand a little bit earlier in like the research side of things and design. And I started trying to look at companies that are more involved with that. So I ended up working at NASA Langley, which is a different NASA site, and it's the first NASA site, actually. It's in Hampton, Virginia, which is near Virginia Beach. And I worked actually for the aerodynamicist that designed the entry system for the Spirit and Opportunity rover. So this is the entry, descent, and landing for the Mars exploration rover. So you can see that this is a space capsule that's heading into Mars's atmosphere. When it actually starts encountering the atmosphere, even though it's thin, you can see it starts generating a lot of heat, it's slowing down rapidly, and it's actually descending from hypersonic speeds down a little bit slower, and then a parachute deploys. And so the parachute's really what starts to slow it down, and in order to have that parachute deploy, your capsule needs to be really steady, on its mark, not moving around a lot. Then actually another parachute deploys, and that little triangle is actually the rover that's contained inside. It's kind of bundled in this, this kind of airbag type system, and you'll see it actually expand in just a little bit. So yep, pops out, little triangle, and then you're actually going to see that start to, that's actually thrust, so it's thrusting down at the ground to slow it as it descends, so even to further slow it down, it releases, and then it tumbles to the ground safely. So all of that is this super complicated series of events. It all has to go perfectly because the margin for error is none. If you don't have something that deploys correctly, you're going to be hitting the surface at hundreds of miles per hour and the rover will basically be dead. So what I worked with my mentor on is how do we predict whether that capsule is going to be stable or not, and we actually did a lot of wind tunnel testing. So I'm not sure if you guys are familiar with wind tunnel testing, but I think it's one of the coolest things in aerospace engineering. And it really allows you to start getting initial information about your vehicle. So I totally fell in love with aerodynamics engineering, ended up wanting to pursue that for my career as well. And I started 2 years ago at Boeing Research and Technology. So Boeing is just about like 10 or 15 minutes away from here, but I love Boeing Research and Technology, or BRNT, for a couple reasons. Boeing is one of the largest aerospace companies in the world. They work on things from commercial airliners, helicopters, fighter jets, satellites, space shuttle, like all the space vehicles, and really what VRNT does is it actually assists things so that VRNT is oftentimes working on things that are 10 to 15 years ahead of production. So we're trying to solve those early technical development questions so that when they go to production, there are no surprises. So Boeing supports all of those different vehicle types, and we really get to touch a lot of the different problems. And I find that there's a lot of variety in that work, and I really love it. How do I get this from paper or a computer to something that can be actually in existence? But 3D printing, it enables you to connect directly to that printer right off the bat, really cheap, really no interface. And there's a ton of different geometries that are enabled by 3D printing. You can get a lot of more complex inner shapes that you wouldn't also do it. And so we're trying to figure out, how do you make 3D printing light? How does it fit into aerospace? And so this is a wing that one of my lead technologists in the group that I work in, he actually designed this airfoil, which is kind of cool. And this is something that was 3D printed, and it's made out of plastic. And so when you 3D print something, you have this little kind of printer head that extrudes plastic material, and it builds up on a plate. So he kind of traced the shape of the airfoil, then it cools, then you build on top of that layer, and you build on top of it. So you can kind of see it's this bottoms-up fabrication. And it's not just plastic, it's metal too, there's tons of different materials, and this is only going to get more and more popular. So if you guys have it in your labs, I totally encourage you to check it out. And another thing that my group is working on is eVTOL, or electric vertical takeoff and lift. Have you guys heard of the air taxi that Uber's talked about, or anything like that? A little bit maybe. So there's this growing problem in cities where they're only going to get more populated, traffic's only going to get worse, it's going to be like in LA everywhere, essentially. And having eVTOL or air taxis would enable you to get from the airport, bypass all that traffic, and save a lot of time. However, these types of vehicles are still very new in their development phase, and so we're trying to figure out, how do you make them safe, how do you make them efficient, and how do you make them battery operated, which is very different for aerospace as well. Alright, so a lot of times we start with people learning about just kind of what makes one of these drones different than a plane. So in this case, our thrust is actually pointing directly upwards. So that's what allows a helicopter, to just stay stationary. A plane couldn't do this. You have, in this case, thrust is going weight. And then similarly, when you want to turn, you don't have ailerons, you don't have rudders. Instead, you're actually using the differential thrust of those four propellers to move you forward, backwards, sideways, and kind of using that going forward. So as I mentioned, I'm an aerodynamics engineer, and so at a basic level, what I care about is making sure that the aircraft has enough lift that goes into the wing design. I want to make sure that the aircraft can maneuver safely. That's in the design of the ailerons, the rudders, the flaps as well, and can basically take off successfully, maneuver throughout its envelope, or its flight path or flight mission. I also am very concerned with making sure an aircraft is low drag. So when people think normally of aerodynamic, you want to have drag as low as possible because you're actually making the propulsion engineer's job easier. So in order for an aircraft to cruise, you need to have thrust equal drag. So the more your drag is, the more thrust that's required, and you're having to make your aircraft engine work harder. Structures engineers are really key in the design of an airplane. In airplanes, they go through a lot of aggressive maneuvers, they're exposed to a lot of really intense forces, and we want to make sure that the aircraft can withstand that and be reliable and have safety and margin. However, in order to make something strong, sometimes you think heavy. But in this case, this is where our structural engineers and material scientists come in, because we want to choose materials that are not only strong enough to withstand the forces of flight with extra margin for safety, but something that's lightweight so we can make the aerodynamics engineer's job easier. So something lightweight, and so that the lift equals weight is a really easy trait as well. So the 787 has 53% composite, which is one of the highest, I think, in terms of aircraft that are flying today. And a composite material is essentially a material that is the fusion of two things that are untraditional, usually involving a polymer. So have you guys heard of carbon fiber? Yeah, so carbon fiber is a composite, and in planes there are a lot of different kind of variations off of this. You have fabric, it's essentially kind of a fabric woven together material, and you have these high strength such as glass or carbon that are fibers, and they're woven with kind of lower density things such as epoxy, different materials in between. And the cool thing about carbon fiber is it is actually higher strength and lighter weight than aluminum. And the catch is, though, that carbon fiber and composite materials are usually not strong in every direction. So if I look at that wing, so a wing is going to be exposed to a couple different stresses. It's going to be exposed to bending, as well as torsion, so twist here. So usually if I were to try and design a material for this, I would want to make sure it's really strong in bending, because those are going to be the highest forces and stresses on the aircraft. But with carbon fiber and composite material, it's going to be weak in one direction just because of how it's built. And you want to make sure that it's appropriate for your application. And so one key example is here in the dark blue. That is a titanium material. And titanium is really strong in all the directions, but it's a little bit more expensive. But the thing is, you need that because that's where the engine mount is, and that's where some of the most intense forces are placed on the aircraft. So a configuration engineer is probably the first person in the design process. And what they do is usually, Boeing marketing will say, okay, I think that there's a really good market. We could sell a lot of planes if we carried this amount of people, we had this range, and we could go this fast. And so what a configuration engineer would take those requirements and actually say, okay, what does my plane in terms of an initial sketch and initial guess need to look like? These configuration engineers are seriously amazing. They are jacks of all trades. They know a little bit about propulsion, they know aero, they know structures, and they do a pretty amazing job of getting close. I think the project I work on, our configuration engineer was so good that we've only had to change things by like 5%. He's amazing. Computer engineers, software engineers have a huge kind of influence and importance in terms of making sure the plane is safe to operate, working in the cockpit, making sure that the pilot's life is easier as well. Another key area is in electronics engineers. Aircrafts are actually only getting more and more sophisticated in this regard. The 787 had more batteries on board than any other aircraft in the past. And so making sure that system is reliable and robust is a huge job of electrical engineers. Manufacturing engineers are a huge portion of the actual final cost of the airframe. And so their goal is to take your particular aircraft, make it and make sure that it looks exactly like the drawing, it withstands all the testing that you put it under, and it's low cost. And so a large portion of the people who are up in Seattle that make Boeing's planes, those are a lot of manufacturing engineers. So I want to go over some influential people in aviation. These are just a couple, but I wanted to highlight, Bessie Coleman, who was named one of the top 100 most influential people in aerospace. She actually was the first African-American woman pilot, and she wanted to become a pilot at a very young age, but nobody in the United States in the early 1900s would train her. So she actually had to go to France to learn how to fly and became one of the best pilots in the United States when she came back. She was part of this flying circus. So you guys know how we have air shows? So they actually used to rotate around the country and became renowned as one of the most fearless pilots out there. And she got a huge name, she got a huge following, and one of the things she wanted to do was actually open up a school for people who could, kind of people of all, kind of all races, genders, to actually be able to learn how to fly, because she didn't have those opportunities. And although she unfortunately died in a plane crash before she could enact that, she hugely opened the doors. She began to gain recognition and realized that despite my race, despite my gender, I can still be a better pilot than a lot of you. And one of the things I just wanted to leave you guys with is, I think when I was at your age, I didn't quite know what I wanted to do. I had a lot of things I thought I should do, but the point is you don't even know now. I think the most important thing, which you guys are actually doing literally right now, is to try and take opportunities to get more acquainted with what, outside of school, in terms of what a career would look like. Try different things, learn what you like and what you don't like, and bottom line is to follow what you're interested in. If you like what you're doing, it's going to be so much easier, because school is hard, and if you like what you're learning, you don't really notice those hours that you're spending on a problem set. However, if you do want to go into aviation, I'm a little biased. I think it's one of the coolest fields out there, and there are so many amazing problems. Hypersonics, air taxis, going to Mars, these are all problems that are hopefully going to be solved in the next 10 to 15 years. And if you guys were to kind of go into the aviation field, you'd be the ones to solve them. So, with that, I want to thank you guys for your time and listening to my story.